This video is part 2 in a series about the Super Nintendo's sound system, the SPC700. In this section, we'll be looking at the SPC700 instruction set. I'll go over some of its benefits and shortcomings, and compare it to the 6500 series instruction sets. Note that this video isn't going to be a tutorial that explains how each of the instructions works. That will have to wait until another video in the future. This is just going to be an overview and reference material. The SSMP processor, along with its timers, counters, and I/O ports, contains an SPC700 series processor core. It supports an address space of 64 kilobytes with a 16-bit address bus. And it uses an 8-bit data bus, so it can send 8 bits of information around at a time. The SNES audio subsystem was probably designed around this. The I/O ports that run to the DSP and the SNES are 8 bits wide, which are perfect for the 8-bit capabilities of the processor. It also has its 64 kilobytes of audio RAM, which constitutes pretty much the entire address space. Were there any other options besides the SPC700 that could have been used? Absolutely. For example, the Sega Genesis also had a separate processor dedicated to handling music and audio. It used a Zilog Z80, another 8-bit processor. Another option could have been an Intel 8080, or say, something similar to the Sharp LR35902 processor found in the Nintendo Game Boy, which is a sort of hybrid of the Z80 and the 8080. And then, since the SNES's main processor, the Ricoh 5822, is based upon the 65C816, it wouldn't be wild to use a 6500 series processor as well. The Ricoh 2A03 was found in the original NES, which was based upon the 6502. Using a 6502 would have allowed for code to be shared between the two processors if that was desired for some reason, since the 65C816 has a 6502 emulation mode that allows it to run code just like a 6502. In fact, rigging up the audio system with a 65C816 of its own would have worked as well, even if it would have been a bit overkill. However, in this video, I'm going to compare against a different 6500 series processor, the 65C02, which is the basis for the processor found in the Atari Lynx. It's a direct upgrade of the 6502, but not so much of an upgrade as the 65C816 is, and I think it will really help highlight the benefits and other differences the SPC700 architecture has compared to the 5822 the SNES has. Before comparing the instruction sets, let's look at the CPU's registers. The 65C02 and SPC700 both have 6 registers, an 8-bit accumulator A, 2 8-bit index registers X and Y, a 16-bit program counter, an 8-bit stack pointer, referred to as S in the 6500 series and SP in the SPC series, and a status register, referred to as P by the 6500s and PSW by the SPC, short for Program Status Word. Like mentioned in the last video, some SPC instructions combine the Y and A registers to make a single 16-bit register known simply as YA, which treats the 8 bits in Y as the high byte and the 8 bits in A as the low byte. The two processors have very similar but slightly different status flags as well. They both have -N, overflow V, break B, interrupt I, 0Z, and carry C flags. The 65C02 has a D flag for toggling binary coded decimal arithmetic, while the SPC700 has a half-carry H flag to aid with BCD instructions. We'll talk about BCD a bit more later on. The biggest difference is that the SPC700 has a P flag, which is used to toggle the direct page. See, we're dealing with a 64 kilobyte address space, so each address needs to be 16 bits long in order to identify each memory location. The 65C02 has instructions that can only target memory addresses located in what is called the 0 page. That is, the high byte of the address is defined to be 0. By doing that, the instruction can use one fewer byte and take up less space overall. The 0 page is where you'd want to put your most commonly used variables. The SPC700 upgrades this concept by being able to toggle between the 0 page and the 1 page, I guess you would call it. If the P flag is cleared, then the high byte of these instructions is defined to be 0. But if the P flag is set, it is defined to be 1. Whichever page is currently active is called the direct page. It should also be noted that both processors define the high byte of the stack pointer to be 1, so if the P flag is set, the direct page will be sharing space with the stack. Let's start filling out something called the instruction matrix for the SPC700. It's just a table that organizes all of the possible instructions that the CPU can execute based on the instruction's opcodes. The opcode being the first byte of the instruction when it's assembled into machine code that identifies which instruction it is and what address mode it will be using, which in turn identifies how many operands there are and what type they are. For example, the opcode 00 corresponds to the NOP instruction, which is short for no operation, so it goes up here in the top left corner. We'll first go through all of the instructions that are shared by the SPC765 CO2, since they're going to be the really standard instructions that are pretty essential for most processors. There is a large set of instructions that I like to call the Big 8 instructions. These are the load value to the accumulator, store value from the accumulator, which in SPC700 syntax are both written as MOV, add to the accumulator with carry, subtract from the accumulator with borrow, compare with the accumulator, logical OR with the accumulator, logical AND with the accumulator, and logical exclusive OR with the accumulator, which is written as EOR in this syntax. As you can see, the accumulator is called the accumulator for a reason. It does a lot of heavy lifting. There are a ton of addressing modes for each of these instructions, but there are 8 that both of these processors have. There's direct page access, direct page indexed with X, word address access, word address indexed with X, word address indexed with Y, direct page indexed with X indirect, direct page indirect indexed with Y, and immediate. The word address modes require specifying the entire 16-bit address location, while the direct page address modes are that shorthand way I just talked about earlier that require only an 8-bit operand. The immediate address mode just treats the operand as the value to be acted upon. The indirect address modes allow for a 16-bit memory address to be stored somewhere in the direct page, and this instruction encodes the memory address of that memory address, sort of like a pointer, which is why they're referred to as indirect modes. You'll see there is one instruction missing here, and that is what would be the store accumulator to immediate instruction, which just doesn't even make sense at all, since the value stored needs to go to a memory address. The next set, which I like to call the small 6, has fewer addressing modes since they aren't as common. These are the arithmetic shift left, logical shift right, rotate left, rotate right, increment, and decrement instructions. These only have direct page access, direct page index with X, word address access, and accumulator addressing modes. The increment and decrement instructions can also act on the X and Y index registers. The index registers also get a few more instructions, including loading and storing. They also have transferring to and from the accumulator, as well as comparing to an immediate, direct page access, and word address access. There are also 2 instructions that transfer the value in the X register to the stack pointer and vice versa, which is the only way to directly modify the SP register. There are a set of 8 instructions to push values onto and pop values off of the stack. The 4 registers you can do this with are the accumulator A, index registers X and Y, and the PSW register. There are the tset1 and tclear1 instructions, which are written as TSB and TRB in the 6500 syntax. These logically AND the accumulator with the value at the specified address, setting all of the processor flags accordingly, but doesn't actually modify the accumulator. Then the bits in the accumulator are treated as a bit mask, and those bits in the memory location are either set for tset1 or cleared for tclear1. Speaking of setting and clearing bits, there is a family of set1 and clear1 instructions that sets or clears just a single bit of a memory address in the direct page. There is also an entire family of BBC and BBS instructions, which are branching instructions. These will branch execution to somewhere else in the code if the specified bit in a direct page memory location is set or cleared. Then we have the standard set of branching instructions, which branch depending on the negative flag, the overflow flag, the carry flag, and the zero flag. There's also a branch always instruction. This is different from the jump instruction, since the branch instruction encodes an 8-bit signed relative offset, while a jump encodes a 16-bit absolute memory address. There is also a jump word address index with X indirect addressing mode, which is good for creating jump tables. There is a call instruction, which is like jump, but also pushes the program counter to the stack, so that it can be retrieved later on with the return instruction. Similarly, there is a break instruction, which fires a software interrupt that pushes the program counter and the PSW register to the stack. The ret-i instruction is used to undo this and return from an interrupt. There are 5 instructions to directly modify some of the flags in the PSW register. Note that the overflow flag can only be cleared and not set, and this clears the H flag as well. Also of note that the EI and DI instructions enable and disable hardware interrupts, but the SMP chip is not connected to any lines that would even allow a hardware interrupt to occur, so these are kind of useless. And finally, we have a sleep instruction, which suspends the CPU and puts it into a low power state until an interrupt occurs to wake it back up again. Which, again, since there can't be any interrupts, ends up performing just the same as the stop instruction, which halts the processor for good until the system is reset. Take a look at the instruction matrix now, and you'll see how it's only about 2/3 full. The remaining instructions are unique to the SPC700. But first, let's take a look at what the SPC700 doesn't have. Here is the instruction matrix for the 65C02, with the instructions we just looked at filled in. They might look a bit different, but that's just because the mnemonics for each of the instructions is different in the syntax. There's also a bunch of opcodes that just aren't even used. This is a big advantage that the SPC700 has in that it has an instruction for every opcode. The 65C02 leaves a lot of them unused, and all of these are just treated as different sized NOPs. But it does have a few instructions and addressing modes that the SPC700 doesn't have. First off, the big 8 instructions have a indirect direct page, or rather 0 page, without indexing address mode. The equivalent code on the SPC700 would require zeroing out either the X or Y register to get the same effect. Similarly, the jump instruction has a word address indirect without indexing address mode. The small 6 instructions, as well as the load X and load Y instructions, have a word address indexed with X, or indexed with Y when loading into X. On the SPC700, you would have to read the memory value into the accumulator, modify it there, then write it back if you really needed the indexing. Also, the TSB and TRB instructions have 0 page access, while the SPC700 is stuck with word address access for its tset1 and tclear1 instructions. The 65C02 has a few instructions the SPC700 just doesn't even have as well. The first of which is the bit instruction. This is just the T part of the tset1 and tclear1 instructions, the part that does the logical AND without overwriting the value in the accumulator. It has 5 different addressing modes. The equivalent code for the SPC700 would just be a logical AND then recovering the value. The second instruction is the STZ instruction, which just stores 0 to the indicated memory address. This just saves having to clobber the value in the accumulator with 0 before writing it like normal. The last two instructions to fill out here are the CLD and SED instructions, so I guess it's time to briefly talk about binary coded decimal. In BCD, 9 plus 1 is 16. Each 4 bits only hold the values 0 to 9. If you look at the numbers in hexadecimal, it will look like it's in decimal. On the 6500 series processors, BCD Arithmetic is enabled by setting the D flag, and disabling it by clearing it. On the SPC700, however, the half carry flag H is what helps with BCD operations. After each addition and subtraction, the H flag indicates whether the result needs to be adjusted by 6 in order for the operation to be a proper BCD operation. The decimal adjustment instructions look at that flag to tell how to work. The DAA instruction will add 6 if needed after an addition, and the DAS instruction will take away 6 if needed after a subtraction. So both processors support binary coded decimal, but implement it in 2 different ways. So let's continue filling out this matrix until we've covered everything. In addition to flipping the C, I, and V flags, there are instructions for setting and clearing the direct page P flag as well. There is also a not C instruction for inverting the carry flag for use in the bit width instructions we'll see soon. The big 8 instructions have 4 extra addressing modes to go with the 8 we've already seen. Those are the X register indirect, immediate to direct page to direct page, and Y register indirect to X register indirect. These last 3 are great because they are memory-to-memory operations. 2 values in memory can be accessed without having to read either of them into the accumulator first. We also see something else that isn't available in the 6500 series instruction sets: register indirect access. This allows a direct page memory location to be held in the X or Y index registers, which becomes the effective address of the instruction. There are also a load and store X register indirect with auto increment. This allows you to march through a data block without having to increment the X register manually every time. We have a handful of 16-bit word operations. These include load, store, add without carry, subtract without borrow, compare, increment, and decrement. These all use direct page memory locations and the 16-bit YA combined register when applicable. There's also the multiply and divide instructions as well. These are nice because the 6500 series doesn't have multiplication or division at all. The SNES's main CPU has to rely on extra hardware within the 5A22 chip that includes memory-mapped multiplication and division registers that you have to write to and read from. We've got expanded width instructions, so we also have diminished width instructions that operate on a single bit. These include load, store, logical OR, logical AND, exclusive OR, NOT, as well as OR NOT and AND NOT instructions. The 5 instructions that operate on the carry flag, along with the not C instruction, ensures that you can get any combination of logic you need with just 1 or 2 instructions. Then we have the XCN instruction, which exchanges the upper 4 bits of the accumulator with its lower 4 bits. Finally, there are a bunch of additional control flow instructions. The table call instruction is a shorthand for the call instruction, where the location of the routine to call is held in a table at address hex FFC0. The table can have up to 16 entries, and each corresponds to its own opcode in order to really reduce the number of bytes used. The special page call instruction is another shorthand for the call instruction, but it's slightly different. Only the lower byte of the routine's memory address is included in the operand, and the high byte is defined to be hex FF. This is kind of similar to how the direct page address mode defines the high byte of the effective address to be 0 or 1. This means with a P call, the routine is located in the hex FF page, but with a T call, Only the pointer is located there, and the actual routine can be anywhere in the address space. The CBNE instruction is a combination of the compare and branch if not equal instructions. It has a direct page and a direct page index with X address mode. And finally, the DBNZ instruction, decrement and branch if not 0, has a direct page and Y index register address mode. These 4 branch instructions are very useful for making tighter loops, which can significantly reduce the overhead when it comes to execution time. And that wraps up all the instructions. All in all, it's a pretty well-rounded instruction set. You have your memory loading and storing and other data movement, arithmetic like adding, subtracting, multiplying, dividing, bitwise and logical operations like AND, OR, XOR, NOT, bit setting, bit clearing, and bit shifting, then stack operations and program flow control. Here are some statistics regarding the SSMP processor. It averages about 260,000 instructions per second when clocked at 1.024 MHz, which, after some analysis from various SNES games, comes out to around 3.9 cycles per instruction. This, of course, would depend on the efficiency of the code that is being run. The lowest cycle count for an instruction is 2 cycles, while instructions like call and multiply and divide take 8, 9, and 12 cycles respectively. For comparison, the SCPU on the Super NES side averages about 800,000 to 950,000 instructions per second, depending on the speed switch, where it's clocked at either 2.68 MHz or 3.58 MHz respectively. Its 65C816 instruction set results in a CPI of around 3.4. Thank you for watching. In the rest of this series, we'll actually be looking into, the audio portion of the audio subsystem. That's what this series is all about, and it's really what everyone wants to see, isn't it? The next video will be about the bitrate reduction sample format, so please stay tuned.